So trig identities, we got into it a little bit last time, but they're basically mini proofs. All right. So, and if you have familiarity with geometry, logic, you might have done a proof, like a 2-column proof. This isn't really that. This is more like using legal identities. And I guess if it's an identity, it must be legal, to prove that the left side of an equation is equal to the right-hand side. All right. So on the previous page, you have the helpful hints. It's actually, I call it helpful hints, but it's more like this is how you do it. All right. So maybe I'll just call that process from now on. Because usually the helpful hints come after you tell somebody how to do something to begin with. All right. So the first thing you're going to do is look for an identity that can be applied. Like, for example, tangent is equal to sine over cosine, or cosine squared plus sine squared is equal to 1. All right. That's all coming from this stuff over here. Now, we tackled really this top block here last time. So the identities that we work on tonight are mostly going to deal with those. All right. You'll also see examples where you have difference of two angles, sum of two angles. These, I would think, if you don't have too much experience with this content, I would think that you're probably going to reference this page pretty frequently. All right. That's typically how it was in the past. But like I said, with the unit circle and even this, the more you commit to memory, the easier math will be from this point forward. All right. So hopefully you took some time between last class and this one. If not, take some time between this class and the next one. And I'll tell you, it's never too late. So you procrastinate, perhaps. I know I do. And you find yourself in the middle of April being like, I don't know any of these rules. It's still not too late. All right. You can get away with referencing these pages, specifically this one, for now. But the further we move away from today, the more you're going to want to have this committed to memory. All right. And, the reality of a class where it's remote instruction, you make it through this class without ever having to memorize those rules. But I'll tell you, it sure makes life easier in terms of being able to tackle this concept. And also anything that emerges from this, because we do this seemingly in this class, like trig identities, we do it and it'll seem like we're doing it for the sake of doing it. Now, some of them are actually kind of fun. Now, you may not necessarily agree with that, but nobody asked for your opinion. No, I'm just kidding. You might not agree with it in the sense that it's the pure definition of fun, like going on a slip and slide or something like that. I find that fun. It's math fun. All right. It's like a puzzle. All right. When you solve one, you feel pretty good about things. All right. If you don't, you know that it's only a matter of time. It's only a matter of finding the right rule before you can figure it out. All right. So we'll start off with I'll call it an easy one. What I like to do is draw what I call an impenetrable barrier. This is the line that you do not cross. And what I mean by that is you don't bring anything from the left side of the equation to the right side of the equation. We're not solving equations here. We're working expressions to find equivalence. All right. So these problems, they're more like self-checking activities to see if you know your rules. All right. Like, for example, cotangent of x. I would ask myself, what do I know about cotangent of x? And the first thing that comes to mind is that it's equivalent to cosine divided by sine. And that may only be because we did a lot with that with the graphs, so it's pretty recent. But, you may look at it and say, first thing that comes to mind is that it's equivalent to 1 over tangent. You might go in a different direction. I would say a good suggestion, I don't know if I put it in my helpful hints area. Oh, I did. Try writing the expression in terms of sine and or cosine. All right. And what I mean by that is whatever rule that you choose to use, if there are multiple, well, actually not even whatever rule, like whatever trig function you're trying to manipulate, look for a rule that'll convert it into cosine and sine, right? And in this case, cotangent is cosine over sine. All right, that's a direct substitution. Cosine over sine is the same thing as cotangent. So this expression here is saying take sine and multiply it by cotangent. I'm looking at it and saying, I'm going to take sine and multiply it by cosine over sine. So you may look at that and say, well, why would I do that? What's the point? Well, the point is to try to simplify. So now that I have it in terms of sines and cosines, if I'm ever going to be able to cancel anything out, it's probably going to happen in this form. So I'm going to take that sine, I'm going to write it as a sine over 1, sine of x over 1. When I multiply, and you don't have to show this intermediate step, but I'm going to do it anyway, just for instructional purposes. You could make sine x over 1 times cosine x over sine x. You can make that sine x times cosine x. 1 times sine x is sine x. Now I see I have a common factor that can be canceled, and I'm just left with the cosine of x. All right, and that happens to be what the other side is equal to. So I have just performed my first proof. I have verified that sine of x times cotangent of x is the same thing as cosine of x. Now, this isn't the kind of thing that you would memorize. I mean, it's a rule. I mean, you could look at it and say, all right, well, now anytime I see sine x times cotangent x, I could just make that a cosine x. Much simpler. It's more so that you're able to, what I highlighted in yellow here, you're able to do that because the rest is just algebra. Now, don't get me wrong, sometimes it's not easy algebra, but it's still algebra, which means that whatever rules you've learned about with algebra, they're still in play, even though we're working with sines and cosines and tangents and stuff like that. So number 2, right out of the frying pan into the fire here, we tend to try to work one side of the equation and go as far as you can with that before moving on to the other side. Sometimes you might want to like alternate back and forth, as long as you don't add or subtract something from one side of the equation to the other, and as long as you don't multiply or divide both sides of the equation by something. Like if at any point you're doing something to both sides of the equation, then you know you're going off the rails, right? So that's why I draw the impenetrable barrier right down the pipe here. And I decide, and you know what? For this part, there's really no wrong answer. Do I want to start on the left side or do I want to start on the right side? I tend to want to start on the side that's more complicated, but you can go either way. All right. So I'm going to start on the left because I see a power of 2 there, which means I can do something with this binomial. So I'm going to rewrite this as cosine x minus sine x times cosine x minus sine x. Let me just move this over, schmidgy. All right, I'm going to rewrite it like that because now I could use the distributive property to simplify. And also, I'm probably less likely to accidentally just take this and raise it to the second power and then take that and raise it to the second power. Okay, that's the most common error when it comes to a binomial squared. People don't realize all the time, or maybe you just kind of like have a brain cramp, but you have to at least consider it as 2 separate factors being multiplied. All right, so I'm going to apply the distributive property. So FOIL method, maybe you learned it that way. Some people call it double distributing. Some people just call it distributing because that's really all it is. I'm going to take each part of the first binomial and multiply it by each part of the second. All right. Now I'm doing this slowly, even though it's it's an old concept. It's just for whatever reason, people are that like they know how to distribute, they know how to factor. It's just when you throw trig in there, people get less comfortable. All right, so I'm going to take this and multiply it by each term over here. So first I'm going to multiply cosine by cosine. So that's cosine squared x. Remember last time I mentioned that when you have something, I'll just say note, where it's cosine with the power of 2, that's the same as saying cosine of x, that entire function raised to the power of 2. These are the same thing, right? It's just this is the more commonplace way of writing it. In a calculator, they tend to want this, right? Which is kind of annoying because a little consistency would be a good thing, all right? So then I'm going to take this cosine here and multiply it by the negative sign. So now I have negative sine x cosine x. Or maybe you like putting the cosine first. So it'd be negative cosine x sine x. Either way, it's commutative. All right. So then I'm going to reset. But I'm going to take the negative sign and multiply it through. So negative sine x times cosine x, just for consistency, I'm going to write the sign first. So negative sine x cosine x. Then I'm going to take this negative sine x and multiply it by this negative sine x, and that's going to give me a sine squared x. And for whatever reason, I can't judge the amount of space I have, so I got to move that over. Sine squared x. All right. The reason why I wrote it this way in the stacked form is so that it's easy to see that these two are like terms. All right. They're made up of the same ingredients. All right. So then I would ask myself, okay, well, what do I get when I put that together? It's still algebra. Can't lose sight of that. I'm actually going to move this real quick. I'm going to tuck in a coefficient here. This is an assumed -1, -1. So when I combine these like terms, I'm going to bring the cosine squared down. But now it's just a matter of keep the variable and combine the coefficients. -2 sine x cosine x. Now, like I said, you want to try to stay on the same side of the equation and just kind of work that all the way through to its natural logical conclusion. But there's nothing wrong with taking a peek at the other side. So I'm looking at this now. And again, my whole goal is to get the left side equal to the right side. I'm looking at this now and saying, well, I got this part. This is the same as that. So if I can get rid of the cosine squared plus sine squared, then I'll be in good shape. So I'm going to rewrite cosine squared x plus sine squared x, then put the -2 sine x cosine x at the end. And my reason for why I'm doing that is just a simple, hey, it's on the end over here. So I want it to be on the end over here. All right. So then I would just be looking for another rule, something that makes cosine squared x plus sine squared x equal to 1. Well, the good news is that is a rule. I'll grab it from up here. The one I have highlighted in purple, and we used A's, but still same structure. And yeah, the cosine squared comes first, then the sine squared, but it's the same thing, same rule. All right. So this is a Pythagorean identity. Cosine squared x plus sine squared x is equal to 1. Now I could just bring everything else along for the ride, and I'm good to go. All right, because now I have direct equivalence from the left side to the right side. So what I like to do, I mean, once you have the left side equal to the right side, you're done. You can just kind of stop. Or if you wanted to work the right side, once that's equal to the left side, you're done. You've proved what needed to be proven. But I like to write a little statement here, just showing that I do have the direct equivalence. All right. And, that's more of a teacher student thing than, like practical way of doing a math problem, because Like, it would be nice for you to tell me, hey, I just recognized that the left side is equal to the right side, and now I know I'm done. As opposed to me looking at it and saying, if you didn't have any of this stuff here, did you realize that they were the same, or did you just stop because you ran out of ideas? So I like to put that little equality statement at the end. All right. And you see here that the big significant ingredient, the formula that was used, was different from number one. Number one, once you realize that cosine over sine was the same as cotangent, you're off to the races. Here, you needed to do a little bit more, right? A little bit of algebra, but then follow that up with the Pythagorean identity, right? So every type of problem, at least the ones that I have here, they bring a little something extra to the party. So each one is a good learning experience. For number 3, again, impenetrable barrier. Now, it may just seem, based off of what I'm doing here, that, hey, I guess you just always start on the left-hand side. I'm starting on the left-hand side because that's more complicated than the right-hand side. If I'm gonna have to simplify something, I don't want to start off with something that's already simple. I want to start off with something that's a little bit more complicated and then go from there, right? Now, one of the strategies is to get it in terms of sines and cosines. Right here, I see a cotangent, just like in number 1. I'm going to make that a cosine over sine. All right, so I have my substitution. Now it's in terms of sines and cosines, which is good. But it's like, okay, then what? Well, algebra. That's what. All right. Once you've done your trig, the only thing standing in the way for you solving the problem is the algebra. So I'm going to take this cosine and put it over a 1, and I'm going to multiply these two together. All right. When you multiply a fraction by a fraction, remember it's top times top, bottom times bottom. So we're looking at cosine squared x over sine x. I still have that other sine x just kind of hanging out. I need to do something with that because somehow this complicated expression is going to clean up pretty nicely. All right. So it's going to become one single ratio. Remember, trig functions are ratios. All right. So it's going to be, I mean, you could look at the cosecant as 1 over sine, but we could also just continue to work the right-hand side and see where it takes us. All right. So I'm going to take that sine and put it over a 1 and get a common denominator. All right. So I'm looking at this and say, okay, well, I want to add fractions. We add fractions by making the denominators equal and then combining the numerators. All right. So I want to make that 1 into a sine of x. So I'm going to do that by multiplying the top and bottom of the second fraction by sine of x. All right. So common denominator would be sine of x. So my numerator over here is still cosine squared. For the second fraction, my numerator is now sine squared. Now that I have a common denominator, I can combine the numerators. So that becomes cosine squared x plus sine squared x over sine of x. And this is what I was talking about before, where, hey, if you know your rules, then you already know what to do next. If you don't know your rules, then you go back to the other sheet, take a look and see if there's anything that could be used. Now, this one should be okay because we literally just use this rule. Cosine squared plus sine squared is equal to 1. Right? So this, by rule, is equal to 1. So now we have 1 over sine x. 1 over sine x is cosecant x. So we have our proof, but you can see here that there were really 3 significant steps. One, recognizing cotangent is cosine over sine. There's algebra sprinkled throughout the whole thing. Another rule is that cosine squared plus sine squared is equal to 1. And then the last thing that came up was that 1 over sine x is the same as cosecant x. All right, so we had a lot of stuff going on with this one. All right, now my impenetrable barrier didn't go down all the way, but like I only really need that in the beginning just to kind of remind myself, stay on one side. All right, but we do have instances where you might choose to flip-flop between the two sides. I'm looking more so at number 6. We'll get there in a few minutes. So just be mindful, it's possible that you're just going to start on one side and then kind of switch over and work the other side a little bit. All right. And we'll see examples of that as we go. Number 4, so far, actually, if you compare it to everything else that's on the page that we've done, number 4 looks like it's the most complicated one. It's actually out of the ones that we did, it's probably tied with number 1 as the easiest. All right. Don't take my word for it. When you distribute out the top, something really nice happens. All right. And one question that I would have is, how did you know to distribute out the top? I always think in terms of opposite operations. If they hand me something in factored form, I'm going to distribute it out. If they hand me something distributed out, I'm going to factor it. I'm going to do the opposite of what they presented because I need to undo what they've done in order to show equivalence. All right. So again, same idea as before. We're going to take this 1, multiply it by 1, and then cosine x. So 1 plus cosine x. Then I'm going to take this negative cosine x, multiply it by 1, and multiply it by cosine x. Oops, sorry. Minus. All right. The really nice thing here is if you remember difference of perfect squares, like if you have something like, I'll just do a quick example. If you have something like 1 minus x squared, which is kind of the same structure as this, you'd factor it to 1 plus x, 1 minus x. All right. This is that in reverse order, replacing the x with the cosine of x. All right. So the good thing is that the middle cancels out to 0. So we're left with a 1 minus cosine squared x over cosine squared x. All right. So far, just algebra. We haven't applied a trig rule. Now, last class, I gave you a rule. We derived it. We came up with it together. That rule was that sine squared x, a rule, sine squared x is equal to 1 minus cosine squared x. Also, cosine squared x is 1 minus sine squared x. All right. So I guess rules. The first one is the one that I can apply here. I can replace the 1 minus cosine squared x with a sine squared x. All right. Now, as long as the powers are the same, top and bottom, the ratio holds. So we know that tangent is equal to sine over cosine. So tangent squared would also be sine squared over cosine squared. All right. So that's kind of like looking at one of the rules that we already know, but in a different way. All right. So maybe it's not tied with number 1. Maybe it's a little trickier, but it's still really one significant trig rule. All right. Whereas questions 2 and 3 had a little bit more going on. All right. Number 5, same idea really as number 3, where I have more stuff going on the left-hand side and not much going on the right-hand side. So I'm going to look at the left side. Penetrable barrier. I'm going to look at what isn't a sine or a cosine and use that. Yeah, this is what I want. And use that information, those transformations, substitutions, I should say, to see if I can grease the wheels a little bit. All right. Cosecant is the same as 1 over sine. Should actually highlight this in different colors. Cosine is cosine. We're good there. Cotangent is cosine over sine. All right, so I got a substitution here and a substitution here. Not much I can do with the 1 minus sine x yet, but the other part of it I can do something, because I can put this cosine over a 1 and multiply these two fractions, this one by this one. You can bring the negative along for the ride or not. It's up to you. It's going to be there anyway. And this would be cosine squared x over sine x. So I still have that 1 over sine x here. All right. We're actually in the home stretch, because what makes this problem a little bit better than number 3 is we don't have to get a common denominator. All right. So I already have my common denominator. Sine x on the bottom, 1 minus cosine squared x on the top. Now, again, if you know the rules, next step is obvious. If not, you have to think back. Oh, do I have a rule that shows equivalence for 1 minus cosine squared x? Fortunately, we just did that. 1 minus cosine squared x, we discovered was sine squared x. So that's what I'm going to do. I'm going to replace it with a sine squared x. All right, so I have another substitution I can make. This becomes this. And the rest is just simplifying, because sine squared x divided by sine x, it's kind of like, for example, if I have x squared over x, that would just be equal to x. All right, and that's because I have x squared as x times x over x. One pair of x's will cancel. That's what's happening here. All right, you don't have to show the intermediate step. It's just algebra. But you should be aware of it. This is the same as saying sine x times sine x over sine x. And we're just canceling the sine x, or one pair of sine x's, right? But you don't have to do this, right? Algebra is algebra, right? It's not part of the proof process. Any algebraic knowledge that you have, you could just apply. You don't have to basically teach me it as you're going. All right, so this becomes sine x. The right side is sine x. And so now we have our proof. Like I said, we don't need this. All right. So number 6, you look at and you say, well, I don't know, do I go left side or right side? And again, it's more about what you can do. Like, honestly, I would say most of the time, I look at a problem and say, okay, I have no idea what to do on one side, but I do have an idea what to do on the other. So let me just go with the side I know, right? And you cross the bridge when you get to it. Eventually, you have to tackle the stuff that you're not as comfortable with, but at least you can get going with stuff that you are. So impenetrable barrier. And by the way, when you go to the more challenging side, odds are you're going to have to do more challenging stuff, which you probably don't want to do, but it's a necessary evil, right? So I'm looking at adding two fractions. And in order to add two fractions, I need a common denominator. All right, so I'm going to rewrite just so I can give myself some more room. And don't be alarmed by the theta. We're going to treat that exactly the same way we treat x. All right, so the first fraction, one of the strategies for a common denominator is just multiply each denominator by the other fraction's denominator. And I put an x there. You see, the force of habit, it's going to happen to many of us. All right. Yeah, so it's theta rather than x. So I'm going to multiply top and bottom of the first fraction by cosine squared. And the second one by sine squared. Now, I tend to kind of leave off the argument when I say it, but I always write it. So there's never an instance where you're just multiplying by cosine squared. Like, I'll say it that way, but it's always cosine squared of something. In this case, theta, but it could be x, it could be y, it could be, well, really anything, right? So I have my common denominator. First fraction becomes cosine squared. Maybe that's why I just say cosine squared, because I almost said x, and it's really a theta. Right? The denominator, cosine squared theta, sine squared theta. Second fraction, sine squared theta, cosine squared theta, sine squared theta. And it really doesn't matter what order you write the denominators in, even if it's inconsistent. Let's say for the first fraction, you write it as sine squared theta, cosine squared theta. You don't then have to write another line where they're reversed just to demonstrate that they're common denominators. Cumulative property, geez, I'm just making stuff up. Commutative property, that I have no excuse for that one. Commutative property tells us that you can multiply in either order and get the same result, right? So I don't care which way I write it, as long as I know that they're equivalent, all right? So on the bottom, I'm just going to pick one form, doesn't matter. I'll use sine squared theta, cosine squared theta. On the top, cosine squared theta plus sine squared theta. And it may seem like I was being strategic in writing the sine squared, cosine squared on the bottom, just because that's how it matched the right-hand side. But honestly, I lost track of the right-hand side a while ago, so I just kind of lucked out. The top needs to somehow become a 1. Fortunately, we have our Pythagorean identity, which tells us cosine squared theta plus sine squared theta is equal to 1. On the bottom, I still have my sine squared theta, cosine squared theta, which is equal to the other side of the equation. And so there you go. All right, so this was an instance where at first glance, it looked like maybe you could go either way. And don't get me wrong, there is a way that you can make the right-hand side into the left-hand side. Because just like I'm replacing every cosine squared plus sine squared with a 1, I can replace any 1 with a cosine squared sine squared. All right, I'm sorry, cosine squared plus sine squared. Right, we could have actually gotten from here to there using that relationship. Right, it really is just a matter of what direction your brain takes you. All right, because your instincts may start you going down one road, my instincts start me down the other. We're both right. It's just we're going to take different pathways to get there. All right. Sorry, a little little schmutz on my screen. So number 7, I mean, I think it's, I want to say obvious that the left side is more complicated than the right, but not really in the sense that it's got more stuff going on. It's just a higher power. All right. So if it's a higher power, that means that there's more room to factor. All right. So I'm going to go impenetrable barrier right down the pipe here. This is a difference of perfect squares. So for example, if I had something like x squared minus y squared, that would factor to x plus y, x minus y. All right. As long as the powers are even, you could use this technique. All right. So what you're doing, just taking you back to early algebra right now, we're taking the square root of the first term. That goes here and here. We're taking the square root of the second term. That's going to go here and here. And we just alternate the signs. All right. That's the relationship between the difference of perfect squares, the really difference of perfect powers, and what the factored form is. All right. So I would do the same thing here. Two sets of parentheses, so 2 binomials. Give myself a little more wiggle room here. I'm going to take the square root of the first term. I'll stay with the same color scheme. Square root of the first term goes here and here. Square root of the last term or the second term goes here and here. And we just make sure the signs are different, 1 plus, 1 minus, or vice versa. So this is going to become sine squared theta, cosine squared theta, cosine squared theta, cosine squared theta. And then you compare that, like I said, you take a little sneak peek from the left side to the right side. I'm looking for sine squared, cosine squared, or sine squared minus cosine squared. I have that. And I would ask myself, if I can just get that sine squared theta plus cosine squared theta to be equal to 1, then I'll have what I need. As it turns out, this is the Pythagorean identity. This is equal to 1. So 1 times sine squared theta minus cosine squared theta. It happens to be exactly what I was looking for. All right. So this one was mostly algebra, and it wasn't even a whole heck of a lot of that. It was mostly algebra, though, with one little trigonometric relationship involved. And that was sine squared theta plus cosine squared theta is equal to 1. All right. I do want to give you some problems to practice at some point, but I wanted to do one where you kind of have to work both sides. Just looking for something interesting. No. I'll just do number 8. You know what I'll do? I'll do number 8. I'll leave 9 and 10 as practice problems that will spiral into next class. And then we'll do some on the next page that involve other rules. All right. So again, impenetrable barrier. Tangent of theta, I can make cosine, geez. Sine theta over cosine theta. Cotangent, I can make cosine theta over sine theta. All right. Now, it's the sum of 2 fractions. So I might go the common denominator route. I could also look at the other side. The other side, cosecant is the same as 1 over sine. Secant is 1 over cosine. And if I put it together, I get 1 over sine theta cosine theta. I can work 2 sides independently of one another as long as I don't bring something from one side to the other. All right. Now, on the other side, I don't have a common denominator. So that's kind of a, I don't want to say like it's going to guide you or direct you to work the left-hand side. I don't have a common denominator, so I know what I can do. I can get a common denominator. I can put these two fractions together. Like that is a strategy that you could use, right? The other thing you could do, and it's not always the most intuitive thing, but remember, we have a rule that says sine squared theta, or sine squared a, plus cosine squared a is equal to 1. Don't get too bogged down with the arguments. Whatever's contained within a trig function, it could be a, it could be theta, it could be x. The relationships are always the same, right? So what I can do here is I can replace the 1 with a sine squared theta plus cosine squared theta. And that would be over sine theta cosine theta. All right. Now you may look at this and say, okay, well, what purpose did that serve? Well, I can break up, just like you get a common denominator to put two fractions together, I can unget a common denominator or break up the fraction. I do that by any pluses or minuses that exist in the numerator. All right, so this would become, if I break it up, I wanted the thinner marker, sine squared theta over sine theta cosine theta plus cosine squared theta over sine theta cosine theta. And then I could simplify. So I'm basically doing what I would do on the right-hand side, but in reverse. All right. Sine theta would cancel with one of these, leaving me with just a sine theta over cosine theta. Cosine theta would cancel with one of these, leaving me with cosine theta over sine theta. Bring the plus along for the ride, and we have equivalence. As long as at any point I make the left-hand side equal to the right-hand side, which is what we have right here, then we have what we're looking for. And that is direct equivalence, left side equal to right side. But again, you may have chosen to work down the left side, getting that common denominator like we did before and going that route. Nothing wrong with that. In fact, that might be the way I would do it. I wanted to make sure I did one where we work both sides of the equation, just so you get an idea of how that would work. But honestly, I would probably work down the left side, simplify until I got it to be equal to the right side. All right. You may not have even done this step on the left side. Maybe you go down and once you get to this step, forget about this for now. Once you get down to this step, you say, oh, that's tangent theta and that's cotangent theta, and show that they're equivalent that way. Right? There's a bunch of different ways that these problems could be tackled. And just because, I mean, if you're sitting there in a room with 5 other people, you might do the problem six different ways and all be correct. Right? So it's always wise to keep that in mind. I'm going to put stars on this. Wise, W-I-S-E, wise, as in the root form of wisdom. Wise is the first word of the day, wise. Right? As in, it would be wise to get to know those rules on page 24, I believe it is, because they're, no, 23, I think. They're going to keep coming back over and over again. Yeah, these formulas, it would be wise to learn these rules. All right. So, page 27, we have some really intimidating looking ones, but these, they're directly related to rules on page 23. Right. And I'm going to write the appropriate corresponding rules here because I don't want to have to keep going, like flipping back to that page and just to say, oh, this is the rule we're going to use. Now let me go down and write it anyway. Right. These are sum and difference identities. Right. So for sine specifically, we have two rules: sine A plus B and sine A minus B. And these are ones that I can tell you right now, even though my teacher said the same thing, like, take some time, memorize these rules. You'll thank yourself for it later. Unfortunately, I didn't end up thanking myself until I became a teacher. So like I was like, yeah, it'd be great if I have enough time, I'll sit down and memorize those rules. I never did. So I understand if you have to reference them. And also, to be fair, if I did memorize them, and I know I didn't, but hypothetically, if I did, I would have forgotten it by the time I was ready to teach it anyway. All right. But the first rule, sine A cosine B plus cosine A sine B, sine A for the minus sine A cosine B, you guessed it, minus cosine A sine B. All right, so it's always in the structure of sine, cosine, cosine, sine. All right, it's just a matter of making sure each trig function gets the argument A and the argument B. All right, so we're going to just do this with X's and Y's instead of A's and B's. All right, so impenetrable barrier. It gets a little tight for this because there's a lot to write here. I'm going to start off at the edge of the paper here and start writing. So I'm going to tackle this one first. You know, let me use my, I'm going to use my highlighter. All right, so this one by this rule, because that's the one with the minus sign in it. So instead of A's, we use X's. Instead of B's, we use Y's. So sine X cosine Y minus cosine X sine Y. All right. For the other one, same concept, different rule. All right, so that's going to be sine X cosine Y plus cosine X sine Y. All right. Now addition is commutative, so you could actually write this one in the reverse. Right. So in theory, I could just write. I wouldn't write this if I were you, but I'll just show you sine X cosine Y plus cosine X sine Y. But it's this that's like terms with that, and this that's like terms with this. So there's actually a couple different ways you can handle this. One would be to stack them up one upon the other. The other, like I was saying, you just write it in reverse. All right, I'll put the cosine A, I'll put this part in the beginning. So cosine X sine Y plus sine X cosine Y. Because this is positive and this is negative, I'll do this in I'll use a yellow highlighter. These two are going to cancel each other out. So I have a 1 sine X cosine Y and a 1 sine X cosine Y. Put them together, and again, these cancel, and you get 2 sine X cosine Y. I'm only suggesting that because it saves you from having to write a little bit more than you probably need to. Now you could look at this and say, all right, well, I never would have thought to do this. Well, to be fair, if that is the case, if you never would have thought to do this, it's probably because you don't know these rules. And I would say it's almost definitely that it's because you don't know those rules. So the moral there is take some time to get to know those rules. It really helps. All right. And again, like I said, because these are commutative, I could do it really any which way. Maybe I wanted to put this in the front and match it up that way. You can go either way with it. You can manipulate any algebraic technique that you use is understood as valid, as long as it is valid, as long as it's the correct algebraic technique. All right, so something to keep in mind. Number 2 goes the other way. Well, actually, that's not true. No, it doesn't. There are some problems where it's already in expanded form and you need to simplify it, but that's not the case here. I just misspoke. Or no, I spoke correctly. I just thought I was talking about something else. All right. So a couple more rules. These are all on page 23. All right. So you also have cosine A plus B is equal to cosine A, cosine B, minus, right? So that's a weird little outcome. So the plus sign here has a minus in the expanded form of the rule. All right, sine A, sine B. And really, if you think about it, just like the other sum and difference identities, but for sine, each function, sine and cosine, is getting an A and a B. It's just how they're pieced together that's a little bit different. All right. So the other rule is cosine A minus B is equal to cosine A cosine B plus sine A sine B. All right. So what I want to do is apply this rule to this part of the identity. And bearing in mind that I may want to work the left side and the right side independently of one another, or I want to do a little on the left, a little on the right and see how it works. All right. But I can do a direct substitution here. Cosine X, cosine Y, plus sine X, sine Y, all over sine X, cosine Y. Now, this goes back to what I was talking about on the previous page. You have a fraction with a plus sign on the top. You can break up the fraction by that plus sign. Right? So this would become cosine X, cosine Y over sine X, sine Y. Sorry, sine X, cosine Y. Plus sine X, sine Y over sine X, cosine Y. All right. I find that a lot of these problems get messier before they get cleaner. That's fairly typical. It's not ideal, but that's kind of how it works. Okay, so if you find yourself dealing with something that's seemingly getting more and more complicated, and you're like, I think I'm going the wrong way. You're probably not going the wrong way. You're probably going the right way. It just isn't going to feel like it, at least initially. So I have a common cosine Y. Common is the second word of the day, as in common cosine Y that I can cancel. Just like I have a common sine X that I can cancel. Common is the second word of the day. We're trying to double up on the words, as you may have noticed. All right, so I'm left with a cosine X, sine X. So cosine X over sine X. I'm also left with a sine Y over cosine Y. Cosine X over sine X is cotangent X. Sine Y over cosine Y is tangent Y. And there's your proof. Now, some cases are easier than others. Some cases, I mean, I'm looking at number 4 because it's right below, but some of them look like one side is already simplified and you really can't do anything else with it. and the other one is where you do all the work, but there's a hidden rule in there. All right, so I'm actually going to do number 4 real quick, and then we'll circle back and grab number 3. All right, so impenetrable barrier. Left side looks like the side that I should be doing all the work on. So I'm going to rewrite that as binomial squared. Oh, it is binomial squared. I'm going to write it as a product of 2 binomials. Be careful about little things, like the last 2 problems that we did had both X and Y in it. This one's back to just X. Little things like that could trip you up too. All right. Distributive property, sine gets multiplied by both parts. So that's going to be sine X. Oh, sorry, sine squared X, sine times sine, plus sine X cosine Y. I just did the exact same thing I told you not to do. Be careful. This is all in terms of X. There's no Y in there. So misspoke. Sine squared X plus sine X cosine X. And then when I distribute this part, I'm going to get sine X cosine X plus cosine squared X. And you may remember this. I mean, we did the same, at least this part of the problem before, right? But it's been kind of a blitz where, we're already like 10 problems in. So you're totally forgiven if you didn't instantly memorize everything that I've said over the last hour and change, right? But again, there's an understood coefficient of 1 here. So that gives me, if I add these 2 together, sine squared X plus 2 sine X cosine X plus cosine squared X. All right. Then I could reorganize and write it as sine squared X plus cosine squared X plus 2 sine X cosine X. We know now, hopefully, and if not, you're going to make it a point to study that. Sine squared X plus cosine squared X is equal to 1. And in fact, this is exactly what we did before, one of the first problems we tackled. And this is where we stopped because this is what was written on this side. So the question is, well, how is this different? Well, I try not to throw around the term common sense. This might be the exception. Like, if somehow the left side needs to be equal to the right side, then this must be equal to that, because the 1 plus is on both sides. And as it turns out, it is. This is the double angle identity for sine. And that's all on page 23. But I'll make a note on the side here. Rule sine 2a is equal to 2 sine a cosine a. All right. So that's another one of those identities. There's more identities for cosine, for tangent, double angles, which is what this is. And the reason, hopefully this part at least makes sense. The reason why it's called a double angle, the A represents the angle. The 2 is saying that we're doubling the angle. All right. Speaking of rules, whenever you see a 2 in front of an angle, there is a rule for it. It's just a question of how far you have to look to find it. It's helpful if you know what the things are called, which is why I reference this over here as a double angle. This is also a double angle. If there is a double angle in your expression, there is a rule that can be applied. All right. The double angle rule for tangent is, let me just throw it right in here, 2 tangent x, well, 2 tangent a over 1 minus tangent squared. All right, so that's me applying the rule. And I'll just show you. It's on page, like I said, it's on page 23. Functions of the double angle right here. All right, 2 tan a over 1 minus tan squared a. All right, so we've actually tackled, and if you look at it, we did all of this last time. We just tackled these two rules and these two rules. We have yet to really dive into these, but now we've tackled this one and this one. So we're actually navigating our way through this page just by learning through examples. All right, we get rid of all these ugly check marks. Well, actually, a couple of them I wanted to keep. All right. So knowing that rule allows me to jump from here right to here.
Professor,
Yes.
I'm sorry. Are we finished with number 4 or?
Yep. Because once we got the left side to equal to the right side, that was it.
I'm still, I guess I'm looking at what I have written and I'm missing something.
Oh, I could leave it up for you.
Is the rule that you're referring to right now, is that 2 sine x cosine x is sine square x? Is that what you're referring to right now?
Sine of 2x.
Sine.
So what I did here was I took this and replaced it with this based off of that rule. All right, this rule over here.
Oh, okay. I guess I need to write that down. I didn't see that part. Okay. Sine. Oh, okay. Thank you.
No problem. Yeah, and so like I was saying before, and the reason why I'm jotting the rules down here is because flipping back and forth between page 23 and this, it's a little much. All right. So for now, like I said, I'm just going to jot the rules down. For number 3, the rule that we want, or the relevant rule, again, is tangent to a. You can call it a, x, it doesn't matter. All right, theta if you want. And that's going to be equal to 2 tangent a over 1 minus tangent squared a. All right, and so by applying that rule to the right-hand side, we actually save ourselves a fair amount of work. Because if I look at the right-hand side and compare it to the left-hand side, I'm really just asking myself, how can I make a 2 into a 4? Well, I would do that by multiplying the top of the fraction by 2. But you can't just multiply the top of a fraction by something without also multiplying the bottom. Now, the bottom is a binomial, so I got to make sure I get parentheses there. The top is not a binomial, so I don't need the parentheses. So 4 tan x up top, 2 minus 2 tan squared x on the bottom. All right, and so now I have the left side and the right side equal to one another. And that's my proof. Now, my lousy handwriting aside, you do have to make sure that you're mindful that sometimes it's the coefficient of a, and sometimes it's the power. All right. And what I mean by that is if I have tangent of 2x, that is not the same thing as tangent squared x. All right. in one case, you're doubling the angle. The other case, you're actually raising the entire function to a power. These are not the same thing, even though when I use my crappy handwriting, this power can sometimes look like a coefficient. That's not the intent. All right, so just be careful about little things like that too. All right, now I'm going to put stars on numbers 5 and 6. And I'm going to just kind of move this somewhere else. Put it at the top of the page. I just don't want people thinking it's part of this solution. All right. So we're going to do a couple problems where we'll throw in some numbers, but we're still going to use these identities. So it's a little bit more of an application of what we were doing. And so it's kind of nice to get some numbers involved every now and again. I mean, I've got my blinking calculator up here, and it's and haven't put it to any kind of use yet tonight. Although sometimes that's a good thing. What we want to do is use these identities to help us solve for exact values of trig functions. All right. You know, like unit circle stuff. I talked about that before. If I know my unit circle, then if somebody says, what is the cosine of 135 degrees? I immediately spit out negative radical 2/2. Right. If somebody says I'll say the sine of 11 pi over 6, I immediately spit out negative 1/2. All right. Not because I have a calculator and I can just type it in quickly. It's because it's instant recall. Right. Trig, if you can take the time, and we don't always have the time, but if you can take whatever time you have and use that time to help memorize some of this stuff, it really does pay off. All right. It's probably like the 5th time I've said that, so I won't say it anymore, but it really is that important. All right. So let's take a look at cosine of 105. It says use a sum or difference identity. All right. So the technique I want to be able to use here involves rewriting 105 degrees as the sum or difference of two special angles from the unit circle. All right. Now this is in degree form. So we want sum or difference of the special ones, 0, 30, 45, 60, 90, $1.20, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and I almost had enough room for 360. I'm going to slide it over. These are all the angles around the unit circle. All right. Now, again, teach this stuff. So I've been rattling these numbers off for years. But if you really can rattle them off that quickly, you're getting there. All right. Start off at 0, increase by 30, 15, 15, 30, and just keep doing that till you get to 360. Increase by 30, 15, 15, 30 every quadrant. All right. So all I need are two numbers from this list that are going to either add to or subtract to equal whatever the angle is in the function. So here I need to get to 105. I'm looking at 45 and 60. All right. Maybe that's not what you want to do. All right. It's up to you. If you could find another pair of values that either add to or subtract to get you that number, like 150 and 45. If I do 150 minus 45, I get 105. All right. So you can go either way with it. The whole idea is to get to those two numbers, though. All right. So I'm going to rewrite this as cosine 45 plus 60. right? I'm leaving off the the degree symbol just for convenience. Technically, I should have them there, but you know, when you write as much using the trig ratios, it ends up kind of being a little much, right? So worst case scenario, just make a note that these are in degrees. Although the problem has a degree symbol in it, so it's a safe bet, right? So what I need is the sum identity for cosine. So again, cosine of A plus B is equal to cosine A, cosine B, minus sine A, sine B. All right. So I'm going to just line up my new statement, cosine of 45 plus 60. And I'm going to let A take on the value of 45. So everywhere I have an A, I replace it with a 45. And I'm going to let B take on the value of 60. So everywhere I have a B, I'm going to replace it with a 60. All right. So this is going to be cosine 45, cosine 60, minus sine of 45, sine of 60. Now, as long as I know what cosine of 45 and cosine of 60 is, sine of 45 and sine of 60, I'll be able to come up with the answer lickety split. All right. Cosine 45, rad 2 over 2. Cosine 60, 1/2. Sine of 45, rad 2 over 2. Sine of 60, rad 3 over 2. Thing about the numworks calculator, and again, just being in a remote environment, like you could use software to help you figure this stuff out. It's not a requirement at this point for you to have. I keep saying it. I already said that. I said it 5 times, and I wasn't going to say it again, but here I am saying it again. For this class, you can get away with it. You can get all the answers right, and it's perfectly fine. There will come a reckoning. You'll get to calculus. You'll need to know this. All right. So keep that in mind. Multiplier fractions, rad 2 over 4 minus rad 6 over 4. And I get, with a common denominator, rad 2 minus rad 6 all over 4. Now, I have my calculator in radian mode. So if I want to be able to handle a problem like this, I need to put it in degree mode or convert the 105 into radians. You can go either way. Just find it's a little more mindless to put it in degree mode in the calculator. All right. So again, you go into your applications menu all the way down to settings. Very first one that you see there, angle measure. And in the upper left-hand corner in the orange strip, you'll see it says DEG. You'll know you're in the right mode. So then I type in cosine 45. Well, I'll put the original problem in. Cosine 105. Numworks is really nice. They get you right to this answer here. They don't show you the steps though. And you're going to have to show the steps for a question like this on the test. And I didn't put an announcement out, but I will. A couple of things. One, the practice test is posted and ready to go. So you can look at that at any time. Just remember the same deal as the last practice test. As long as you check all the boxes at the end, you get full credit. Doesn't matter whether you submit answers to the practice test problems or not. That doesn't affect your grade. If you want to submit anything work-wise so that I can have a look at it and give you feedback, you're welcome to do that. Just send me an email and say that's what you're doing, right? Because otherwise I won't think to look, right? Also, officially, the test will be next Monday, so a week from tonight. So we'll do a little bit more new stuff on Wednesday, and I'll leave some time for you to ask questions. But then the test will be next Monday. So if you have, I know some people have accommodations. If those people can just remind me what they are so I can set it all up. I think I know, but I want to play it safe. That would be good. And also, while I'm doing the housekeeping stuff, just a reminder, I hope this doesn't really apply to anyone. I don't think it does, but I am required, and I think it's a good idea to tell you or remind you that tonight is the last day to withdraw from the course, if that is something that you're looking to do. I mentioned this previously a couple times, I think, but the way I have the grading system in this class and all the incentives, you're always in it. So the hope is that there isn't a bunch of people that want to withdraw. I typically don't have many people withdraw from the course, any course that I teach, because my grading system always allows for some hope that you can pull it together, even if you're struggling a little bit early on. Yeah, so that being said, if you're really concerned, reach out to me, send me an email, definitely before midnight, and or we could talk at the end, and I can give you a sense of where you're standing in the course. All right. But one more problem. I won't do the half angle identities tonight. And in fact, well, I'll talk more about that later. I wanted to tackle the sine of 75 degrees. All right, so this is a sine problem. Again, the goal being to find two angles that'll add to 75 from our special angle list. All right, and so I want 75, 30 and 45 will do the trick. All right. Maybe you want to do 120 minus 45. That'll get you to 75 also. All right. So really, it's just like the identity proofs. You can go a couple of different ways, but I'm going to go with the simpler pathway, sine of 30 plus 45. Again, the rule, some identity for sine. Sine of A plus B is equal to sine of A cosine of B plus cosine A sine B. I'm going to swap out every A for a 30 and every B for a 45. So sine of 30 plus 45, sine of 30, cosine 45, plus cosine 30, sine 45. And again, just like I was saying before, if you know your trig facts, unit circle, i.e. unit circle, then you go right through this and say, okay, well, that's obviously 1/2, obviously radical 2/2. But until you get to the point where you know those rules, nothing's obvious, right? So you'll reference the unit circle from time to time. You'll go to the calculator, but you're going to make it a point to try to memorize this stuff. Cosine 30 is radical 3/2. Sine of 45 is radical 2/2. Rad 2 over 4 plus rad 6/4 gives me rad 2 plus rad 6 all over 4. And NumWorks will check for you. So I'll put in sine of 75, lock it in. Yeah, they put the radical 6 first, but who cares? It's commutative. You can add in whatever order you want. All right. If you're really in doubt, on tests, weird things can happen. Like we've all been there, where when you took the test, you were absolutely sure that you did that fine detail that you always do, but for whatever reason you didn't. It's just the kind of stuff that only happens on tests. Okay, I don't like the parentheses. I just need them to make a fraction, but you can see the decimal are the same. Decimal values are the same. So we're good to go there. Next class, we'll do some trig equations. Nothing too crazy. A lot of calculator work. I mean, there's a lot of algebra that you can do with trig equations, but I'm going to show you. I'll show you by hand, and I'll show you using the trig functions in the calculator how you can get the answers, and then I'll let you pick whichever way you want. I'm not going to, for trig equations, I'm not going to make you solve it algebraically. The calculator is just fine. All right. But more on that for next time. All right. So I am going to stop the recording.